You ever stop and wonder how your phone can send and receive signals like billions of times a second without a single hiccup? Well, it's not magic, but it is pretty close. It's all thanks to this tiny, brilliant circuit called the phase-locked loop, and it's basically the hidden engine of our entire modern world.
I mean, just think about that for a second. Your phone, your Wi-Fi router, even your car's GPS. They're all humming along, built on these signals that are vibrating billions of times every single second. So how in the world is it possible to maintain that insane speed with, rock-solid precision? The answer is just a really, really elegant piece of engineering.
See, to move these huge amounts of data through the air, we need signals that are two things. They have to be incredibly fast, and they have to be perfectly stable. And right there, that presents a huge challenge.
The problem is, speed and stability don't really like to go together. You know those super high-frequency signals we need for Wi-Fi or 5G? They're really powerful, sure, but they're also kinda unstable. They have this tendency to just drift off course, which for us would mean dropped calls and, endless video buffering. Nobody wants that. And this really gets to the heart of the problem. On one hand, you've got these crystal oscillators. Think of them like a perfect metronome, incredibly stable, just tick-tock, tick, but way too slow. On the other hand, you have high-frequency oscillators. Now these are like a race car engine, unbelievably fast, but totally unstable. So the big question is, how do you get the speed of a race car with the precision of a metronome?
Well, you do it with one of the most clever circuits ever designed, the phase-locked loop, or PLL for short. This is the ingenious little solution that bridges that massive gap between speed and stability.
At its core, a PLL is basically a self-correcting feedback loop. Its entire job is to look at a stable, slow signal, then look at a fast, kind of drifty signal, and then just force that fast signal to march in perfect, synchronized step with the stable one. It's like a tiny electronic synchronizer.
Okay, so the best way to really wrap your head around how a PLL works is to stop thinking of it as a circuit and start thinking of it as a tiny electronic orchestra.
In this little orchestra, every single component has a critical role to play. So, let's meet the players.
First up, we've got our star musician, the voltage-controlled oscillator, or VCO. This is our race car engine. It's a brilliant performer, capable of playing notes at unbelievably high speeds. We're talking billions of notes a second. But, it can sometimes rush or drag the tempo if you just leave it on its own.
Now, to keep our musician perfectly in time, we have the metronome. This is our stable, low-frequency reference signal. It provides that unwavering, perfect beat that the entire system is going to be built around. It's the absolute source of truth for our timing.
And of course, every orchestra needs a conductor. In a PLL, that's the phase detector. Its job is to listen to both the metronome and our musician at the exact same time. And if the musician gets even a tiny bit ahead or behind the beat, the conductor hears it instantly.
But the conductor doesn't just start yelling directions, no. It makes this gentle, corrective gesture. That gesture, that's the loop filter. It takes the error signal from the phase detector and smooths it out into a really steady instruction, a control voltage that tells the musician precisely how to adjust. Hey, speed up a little or slow down just a touch.
So, how do all these parts actually work together? Well, they form this continuous, elegant feedback loop that is always striving for perfect harmony, a state that engineers call lock.
It's this constant cycle. The conductor listens. If there's an error, it calculates a correction. The filter smooths that correction into a gentle command. The musician adjusts its speed based on that command. This reduces the error, and the whole process repeats thousands of times a second until the musician's timing is perfectly and permanently locked to the metronome's beat.
But here's where it gets even more clever. See, the goal isn't just to match the slow metronome. The goal is to create a high-frequency output that's just as stable. The PLL actually lets the output be a precise, stable multiple of the reference. And this is done with one final, absolutely crucial component, a frequency divider. Think of it like a piece of sheet music. So instead of just playing one note for every tick of the metronome, the music tells our musician to play, say, 1,000 notes. The PLL then locks the musician to this much faster rhythm, but with the exact same perfect stability. And that is the secret to generating a gigahertz signal from a simple megahertz reference. So why does all this matter? Well, because this tiny electronic orchestra. It's the unseen engine driving our entire digital world.
I mean, just think about your smartphone. There's a PLL in there that synthesizes the exact frequency to connect to a cell tower. There's another one that generates the master clock signal that synchronizes the entire processor. They are literally everywhere, performing these critical timing tasks silently and just flawlessly.
Let's just take a number. How about 2.4 billion?
That's the frequency, 2.4 gigahertz, that your Wi-Fi router uses. Right inside that little box is a phase-locked loop, taking a stable but much slower reference crystal and multiplying it up to exactly 2.4 billion cycles per second, and just holding it there, without wavering, so you can stream whatever you're watching right now.
So yeah, the next time you use any piece of modern tech, just remember that microscopic conductor humming away inside. That's the phase-locked loop, making sure all the impossibly fast parts are working in perfect time, creating the high-speed harmony of our digital lives.
Kind of makes you wonder, doesn't it? What other invisible conductors, what other elegant solutions are out there quietly orchestrating the world all around us, just waiting to be understood?